Space isn't silent. It's just not built for our ears. Out between the planets, there's almost no air, no dense gas to carry pressure waves, but everything still vibrates. Magnetic fields hum, plasma crackles, planetary crusts ring like bells. With the right instruments, those invisible ripples become sound. Aboard the research vessel Aurora Array, 3 scientists are halfway through an 18-month mission. Build the first complete acoustic and electromagnetic profile of every major world in the inner solar system. It's supposed to be low-drama, high-precision science. They expect data, papers, maybe a few conference talks. None of them expects to find something listening back. Mira Kowalski is an acoustic physicist who grew up with progressive hearing loss. By 18, most of her hearing was gone. A neural implant gave a version of it back. Sound as patterns on a haptic vest and pulses of color over her vision. Sound for her is survival and identity, proof that there are other ways to experience the world. She's obsessed with one question. What does the cosmos sound like when you're not limited to human ears? Every week, she beams compressed sound data, not just to mission control, but to her younger sister Maya, fully deaf, and an artist who turns spectrograms of planetary vibrations into paintings. Rafael Ortiz is a plasma physicist who grew up in the Andes, listening to thunderstorms roll through the mountains. His grandmother used to say the thunder was the voice of the mountains, arguing with the sky. When he was 19, an earthquake triggered a landslide with no warning and killed her. He has spent his life trying to understand the forces that break worlds and to find patterns in chaos before chaos wins. Sam Park started as a touring musician in underground electronic scenes. The most interesting sounds weren't from instruments, but from misbehaving gear, dying amplifiers, feedback loops, strange electromagnetic interference. They turned to engineering, convinced that data has rhythm, that if you give them any data set, from seismic traces to magnetometer logs, they can reveal a hidden music inside. On this mission, Lena captures the physics of sound and vibration. Raphael listens to plasma and fields, and Sam turns raw numbers into sound. Together they think they're creating humanity's first full soundscape of the solar system. Instead, they're about to rediscover something that may have been left here long before humans existed. They start at Mercury. The small, airless world has almost no atmosphere. If you stood there without a suit, you'd hear nothing but your own breathing and suit systems. But rock still vibrates. Mercury is constantly peppered by micrometeorites, and the sun's intense, uneven gravity tidally kneads its interior. Raphael drops a penetrator seismometer into the regolith. The impacts and slow interior creaks produce vibrations with periods of seconds to minutes, too slow for human ears. Sam compresses the timeline by a factor of 10,000, preserving the frequency relationships but speeding them into the audible range. What emerges is a high, crystalline chime, like tapping a flawless glass bowl in a vacuum. This is what a rock under stress sounds like, Lena breathes. A bell at the edge of the sun, ringing for 4 billion years. Lonely silver and pale blue spill across her visual implant. She asks Raphael quietly whether it bothers him that the planet is so alone. He looks from the data to the blazing sun. Maybe, he says, or maybe Mercury is content. Humans equate silence with loneliness. Mercury might experience it as peace. Venus is next. It's the densest atmosphere of any rocky planet, 90+ bars of pressure, lead melting temperatures, sulfuric acid clouds. Hellish, yes, but acoustically rich. Lena builds a model from Soviet Venera lander data and modern orbiter measurements. Sound on Venus travels through hot, dense carbon dioxide. Low frequencies travel far. High frequencies are quickly absorbed. Wind doesn't whistle. It groans like immense machinery buried in fog. Lightning doesn't crack but blooms into crushing, sub-bass detonations. Sam listens to the simulation and says it feels like being underwater during a storm. Everything's slowed and swollen. As Lena explores the data, she notices a faint, repeating harmonic structure that doesn't match any modeled meteorological or volcanic process. A global-scale oscillation repeating every 41.3 seconds. It's too regular, too coherent. She flags it as anomaly V1. Raphael's eyes linger on the pattern longer than he admits. He calls it an unexplained resonance and suggests they move on. Back at Earth, the team uses long radio antennas to listen to the magnetosphere rather than the air. Charged particles trapped in the Van Allen belts spiral along magnetic field lines, emitting very low-frequency radio waves. Shifted into audio range, these emissions form chorus, eerie, rising chirps and whistles like birdsong in a haunted forest. NASA has recorded these before. Now, Sam and Raphael are doing it live. Lena closes her eyes as her vest pulses in waves and blue-green arcs play across her vision. "This is the sound of home defending itself," she whispers. Plasma slamming into a magnetic wall, and the wall singing back. While she's immersed, Raphael notices a faint, steady beat embedded in the chorus, a pulse every 59 seconds, not synced to Earth's rotation, day-night cycles, or known solar activity. They log it as anomaly E2. When Sam overlays the Venus anomaly and Earth's, he finds that the periods are in roughly a square root of 2 ratio. They don't call it a message. Not yet. But no one in the cabin quite believes it's a simple coincidence. Mars should be nearly silent. Its atmosphere is thin, about 1% of Earth's surface pressure, and mostly carbon dioxide. Mars has no global magnetic field, only remnant patches in its crust. Still, Perseverance's microphones have recorded the papery hiss of Martian wind, the tiny ticks of dust hitting the rover, the sharp snaps of a laser vaporizing rocks. Sound there is weaker, slower, muffled. A human voice would be quieter, lower, and quickly swallowed. Lena pulls seismic data from NASA's InSight lander, which recorded Marsquakes before its mission ended. She speeds up a magnitude 4 quake and reveals a dry, distant rumble, like a heavy truck on gravel but gone too soon, eaten by silence. "Mars has quakes but no tectonic plates," she says. "It's just cooling, contracting, an old house settling." Raphael's magnetometer shows almost nothing. Mars lost its magnetosphere long ago. Out of habit, he runs a long-period spectral analysis on ionospheric data anyway. Buried deep in the noise, he finds a faint modulation with a period of about 91 seconds. He checks, rechecks, and turns pale. Venus's period is 41.3 seconds. Earth's is 59. Now Mars adds 91. They are distinct, non-harmonic values, yet they suggest structure. "These aren't random," Lena says quietly. "They're primes, scaled by some base interval." Sam, half joking and half afraid, calls it a breadcrumb trail across the inner solar system. When they reach Jupiter, they confront outright chaos. The gas giant's magnetosphere is colossal, its radio storms driven in part by Io's furious volcanism. The data stream from a Juno-like orbiter below is a roar of electromagnetic noise. Sam maps field strength to low drones, electron flux to grinding static, lightning spikes to explosive percussion, and produces a terrifying, beautiful soundscape that feels like a planet-sized church organ played in anger. Lena's implant almost overloads with color until she turns it down. Raphael digs through the low-frequency bands beneath the storm. There he finds another modulation, a subtle periodic pattern with a 132-second period riding on top of the natural emissions. They log anomaly J3. Sam aligns all 4 anomalies: Venus 41.3, Earth 59, Mars 91, Jupiter 132, correcting for signal travel times and orbital geometry. The pulses line up into what amounts to a chord, multiple slow beats interlocking in simple mathematical ratios. "This is a chord," Sam whispers. 4 planets, 1 pattern. Lena says aloud what they've all been thinking. This doesn't look natural. Raphael wants to believe there's some unknown resonance mechanism, solar wind physics, magnetosphere-ionosphere coupling. But he doesn't believe in long chains of perfect coincidences, and these periods are too neat. They continue to Saturn. The rings act like a giant seismograph, their density waves driven by oscillations deep within Saturn's interior. Cassini saw those ripples. Sam converts ring wave patterns into sound, a delicate harp of plucked ice, underlaid by a soft organ-like hum. Compared to Jupiter, it feels like a lullaby. Titan adds another voice. Thick nitrogen air, lakes of liquid methane and ethane. Simulated wind there is slow and heavy. Waves slap onto shore with a thick, syrupy sound. A human voice would drop in pitch and sound padded, as if singing in a dream. Raphael analyzes Saturn's magnetospheric data and finds yet another anomaly, this time a 189-second periodicity. Now their list of anomaly periods reads 41, 59, 91, 132, 189. The gaps between them are not uniform, they widen. Fitting a curve through the points, Lena sees the next predicted period would fall between Mars and Jupiter, right where the asteroid belt orbits. There's no planet there, Raphael says automatically. Not anymore, Lena answers. They steer Aurora Array into the belt, a sparse graveyard of rock and metal. The total mass of all the asteroids is only a few % of Earth's moon. Most current theories say the belt is a failed planet, material that never coalesced because of Jupiter's disruptive gravity. Some older theories suggested it might be the debris of a shattered world. Lena's question is different. Regardless of its origin, could there be a coherent pattern in how this rubble vibrates or moves? They deploy a swarm of tiny probes that land on different asteroids and listen. At first, the recordings are unremarkable. Random creaks as rocks warm in sunlight and contract in shadow, clicks from micrometeorite hits, electrostatic pops from charged dust. Lena looks not for quick, loud spikes, but for slow, faint rhythms on timescales of many minutes. She stretches the data, runs long-period Fourier transforms, and eventually sees an almost imperceptible bump. There is a modulation with a period of about 270 seconds, 4.5 minutes. Enhanced and sped up, it sounds like a deep, distant heartbeat with a faint, rising overtone on each thump. They log it as anomaly B5. Sam plugs 270 into their sequence, 41, 59, 91, 132, 189, 270. The ratios between these numbers line up with prime progressions and square root relationships. Plotted in frequency space, they trace an elegant spiral. This isn't weather, or just orbital mechanics, or crust cracking, Raphael says aloud. It's a meta-resonance, a pattern woven across multiple planets and fields. Looking out at the drifting rocks, he adds, shaken. This was tuned. They pieced together a theory. Long ago, in the orbit now occupied by the belt, a real planet likely formed. Oceans, continents, atmosphere, perhaps life, perhaps intelligence. Over eons, its gravity, magnetic field, and orbital motion subtly influenced neighboring worlds. Its tides, the way it tugged on Mars and Earth and even on Jupiter and Saturn, left minute imprints on how those worlds' fields and interiors vibrated. At some point, its inhabitants may have realized that their world wasn't a closed system. It participated in a system-wide music of orbits, tides, magnetospheres, and atmospheres. They learned they were part of a choir, not a solo. Instead of sending radio beacons that would fade or building monuments in stone that would erode, they began to shape that choir intentionally. Very slowly, using whatever means their technology allowed, they adjusted resonances, modulated fields, and encouraged specific global-scale oscillations. They etched the fact of their existence into the dynamics of the whole system. When they understood that their world was doomed by collision, runaway climate feedback, internal collapse, they finished the work. The planet itself may have shattered, its fragments dispersing into the belt, but the pattern they had shaped persisted, encoded in tiny anomalies in field lines and sonic fingerprints spread over neighboring planets. Venus's pressure oscillations, Earth's magnetospheric chorus, Mars's tenuous ionosphere, Jupiter's radio storms, Saturn's ring-driven seismology, and now the subtle heartbeat of the belt. Lena thinks about making art for an audience that may never hear it. They knew no one from their world would ever hear this, she says softly. But they made it anyway, because saying we were here mattered. She touches her implant. She understands that impulse. They package everything they've found, the raw data, the processed sonifications, the anomaly timing sequence, the tentative theory about a lost tuning civilization. Sam also composes one more artifact, a 20-minute piece, built entirely from real planetary data, moving from Mercury's glass chimes through Venus's dense groans, Earth's choruses and Mars's whispers, Jupiter's terrifying organ and Saturn's harp, ending with the slow ghost heartbeat of the belt. They beam it all to Earth. It will take about 18 minutes for the signal to arrive. So what would you actually hear if you could stand on these worlds? On Mercury, you'd hear nothing through the vacuum, but if you put your gloved hand or a sensor against the ground, you could feel a thin, high chime when micrometeorites strike, Mercury ringing like a fragile bell under constant bombardment. On Venus, wrapped in a suit sturdy enough to survive, you'd hear thick, suffocating sound, endless low rumbles from distant storms, deep detonations of lightning that you feel more in your bones than your ears. Everything would be muffled and heavy. On Earth, you already know the surface soundtrack: wind in trees, waves on shores, human voices and machines. Above the atmosphere, though, instruments add another layer, the eerie magnetospheric chorus, a hidden electromagnetic music that has been playing for billions of years while life evolved below. On Mars, the wind would be faint and papery, grains of sand ticking against your suit. Your voice would sound softer and deeper, oddly distant, swallowed quickly by the thin air. Occasionally, you might sense a subtle tremor underfoot as the planet continues its long, slow cooling and contraction. In the upper reaches of Jupiter's atmosphere, if you somehow floated in a reinforced balloon, you'd be immersed in howling winds, jet stream roars, and lightning so powerful its thunder would make your chest vibrate. Above that bedlam, instruments would reveal radio emissions screeching across the spectrum, the giant's true voice expressed in fields rather than air. On Titan, Saturn's largest moon, slow, heavy breezes would push against you. Waves of liquid methane would slap onto rocky or icy coasts with a thick, syrupy sound. Your voice would be pitched lower by the cold, dense nitrogen atmosphere and would feel padded as if coming from across a soft, enclosed room. In the asteroid belt, your helmet speakers would be almost silent except for your own systems. Occasionally, you'd hear tiny pings as dust faintly taps your hull. Meanwhile, seismometers and magnetometers would pick up that slow 270-second rhythm, the barely audible heartbeat of a world that no longer exists in one piece. Every planet's sound is a record of how the universe chooses to vibrate there, in gas, rock, plasma, magnetism, and perhaps in rare cases, in memory. If our solar system truly carries the last song of another civilization, that would mean we live in a graveyard that is also a monument, surrounded by instruments they spent ages tuning. What does that make us? The next verse in a cosmic symphony, new composers learning the instrument we've inherited, or just another brief silence between long, patient chords? The aurora array coasts among the rocks as the data races home. Around the small, bright sun, the planets continue along their orbits, humming their complex, interlocking tunes. Far away, other stars shine, surrounded by their own worlds and fields and vibrations. The universe was never silent. We just hadn't learned how to listen.